Hello, welcome to our lesson on average rate of change. So the rate of change for a function is something we looked at in the previous topic. It's slope. If we were to get technical with the definition, we would say that the rate of change for a function is describing the rate at which the outputs are changing in relation to the inputs. But if we are looking at the rate of change in outputs to inputs, we could say the change in y over the change in x, the rise of the run, it's just slope, okay? So rate of change is a fancy way to say slope, but that should make sense. We've already examined how that's a rate at which we move between one point to the next. Now, if we're looking at a linear function, which is, again, what we did in the previous topic, then the rate of change between any 2 points is going to be constant. So you can pick any 2 points on the graph of your linear function or any 2 points on your line and calculate the same exact slope. However, if your function is not linear, so for anything else, any non-linear function, your rate of change is not constant. It will vary depending on what kind of function you're looking at and where you are on the function. So the best we can do is estimate a rate of change by calculating an average over a specific interval. So we estimate it by calculating an average rate of change. Okay, so when we're calculating this average rate of change, again, this can only be done over a closed interval. That means, like, even just looking at this graph here, the rate of change over this section is clearly negative, and then we turn, and then the rate of change over this section is clearly positive. So I'm not going to be able to average out the rate of change for this entire graph, but I can section it off. And so if I'm looking at a particular interval, which is what I'm going to have to do, I will calculate an average rate of change for that interval. So when we say a closed interval, that means a specific included starting x value and a specific included ending x value. So from what x value to what x value is the frame of reference where we are looking to estimate an average rate of change. And the way we do this, the way we estimate our average rate of change, is using what we call a secant line. So I introduced a tangent line to you in the previous topic. A tangent line is going to intersect a curve at one point, at a single point. A secant line is a line that intersects a curve at 2 points, and you probably could have guessed based on the picture there. And now I'm going to say something that's going to sound a little confusing. I went back and forth on how to word this, but basically, the slope of the secant line through the endpoints of the curve on the closed interval we're looking at is the average rate of change for the curve on that interval. Okay, so let me go to the picture and try to unpack that statement. If I wanted to calculate an average rate of change for some curve, again, that isn't linear, where the rate of change varies depending on where we are on the graph, I have to first say, okay, here's where I want to calculate my average rate of change. So in this picture, let's say I wanted to calculate my average rate of change over this interval. So from this point here, let's just say that this is some starting x value of a, to this point here. And let's say that this is some ending x value, let's just call it b. So that would be the interval where I want to focus. Over that interval, I can see my rate of change is a little negative here, and then it turns, and then it's positive here, but mostly positive. So if I was to average out that slope, that average rate of change, it's probably going to be positive. Now, how I actually calculate my average is using a secant line through those endpoints on the curve over the interval I'm looking at. So again, here's the interval of x's that I'm saying, this is my frame of reference, this is the interval I want to look at. This is the endpoint and the endpoint. These are the two endpoints on that interval. If I draw a secant line through those two endpoints, this is what I have pictured here in blue, finding the slope of that secant line will represent the average rate of change of my curve on that closed interval. So the secant line is what we're going to find the slope of. So we're just finding the slope of the line. Now, if I'm going to call my interval a to b, so call the first x value a, call the second x value b, that's the bottom of my slope function, right? That's the run, that's the change in the x values. But I also need on the top of the slope function or formula, the change in the y values, the change in the outputs. So what would the corresponding outputs be? Well, here, this is some function which I in a very tiny font called f of x. This would be f of a. So whatever this input is, I have to input it into my function to get the output, and that's where it would show up. And then here, okay, if this is my input b, my output would be found by plugging b into that function. So f of b, again, inputting b there. So those 2 points, again, a and f of a, and then the second point, b and f of b, I'm going to use those 2 points to find my slope. Sometimes I'm doing this with a picture, sometimes I'm doing this with an equation, but in either case, it's just slope. So it's the slope of the secant line that passes through the endpoints of the curve on the closed interval we are looking at. And that sounds really technical, but honestly, it's just slope, okay? So here's how we're going to define rate of change again. It's average rate of change because it's approximating what's happening for a curve that doesn't have a constant rate of change for our function over some closed interval, and it's the change in those x values on the bottom of the fraction and the change of the y values in the top of the fraction. Slope, just how we've seen it before with maybe some different notation, okay? So let's try this out. For example, here in number 1, we're going to try to find the average rate of change for this parabola over the interval -2 to 4. So this is the interval. This is my frame of reference. This is the domain. This is the x values where I'm looking. So on the x-axis, I like to use this as my guide. I am looking from -2 to +4. That's the interval. So what I need are the endpoints of my graph on that interval. So on that interval, the first endpoint of my graph is right here, and the second endpoint is actually the end of the interval. It's right there. So the secant line that would go through these 2 points, nope, I thought it was going to make a straight line for me, but I have to put my draw tool on. That's pretty good. So this slope of this secant line would represent the average rate of change over that interval. So I have a couple of options for finding the slope of that secant line. Well, since it's on the graph, it really wouldn't be too hard to just count my rise and my run. So I can see from left to right that I have to rise 3, and I have to run 1, 2, 3, 4, 5, 6. So I can see just by counting my rise and my run that my slope would be 3/6 or 1/2. I also, if I don't like to count, maybe I just can't read the graph, or maybe sometimes I just miscount boxes because my experienced eyes are bad. I can also just use the endpoints and the formula. So the coordinates here are at an x value of -2 and a y value of -3. And the coordinates here are an x value of 4 and a corresponding y value of 0. And notice, again, that the x values, oops, that's my eraser, that the x values here, those are the x values that were in my interval. Okay, all I did was use the graph to find the corresponding y values. So if I wanted to just use my formula, right, y2 minus y1 would be 0 minus a -3. x2 minus x1 would be 4 minus a -2. And I get +3 on the top, +6 on the bottom, and +1/2. And so that's my slope, whether we want to count it on the graph or use the formula. It is the slope of that secant line that is representing the average slope of that curve over that closed interval. Okay? And that sounds really technical, but remember, what I'm trying to do is prepare you for calculus, where you're going to hear a lot of this technical language, okay? And it hopefully makes sense that the slope here is positive. So in this parabola, over this interval, we have a decreasing portion here, but most of the graph over this interval is increasing. So positive sort of makes sense for an answer, okay? So let's try it again, or if you're feeling confident, maybe you want to pause the video and give this a try. On number 2, this looks like an exponential function. We're going to try to find the average rate of change over the interval from 0 to 3. So remember, this is our interval of x's. That's the domain where we're looking. It's our frame of reference. So I'm going to use my x-axis as my guide. So from x equals 0 to x equals 3, this is the interval I'm looking at. So I want to find the endpoints of my graph on that interval. So on that interval, we're here, and let me just drag all the way up to here. So those are the endpoints of my graph on that interval. That is the piece of graph that I'm trying to find the average slope for. And I can do it by finding the slope of the secant line that goes through the two endpoints on that interval. So this line right here, well, let's just pretend. No, I'm going to try it again. Terrible. One more try. Nope, it's just getting worse. Okay, that's better. So if I find the slope of this secant line, the secant line that goes through the endpoints on the closed interval I'm looking at, the slope of that secant line represents my average rate of change for my curve over that closed interval. So since I have the graph again, I can just count my rise and my run to get that slope. So from here to here, to get from my left point to my right point, I have to rise 1, 2, 3, 4, 5, 6, 7. And I have to run 1, 2, and 3. And so I can tell just by looking at my graph again that my slope is going to have a rise of 7 and a run of 3. So 7/3 is my slope. Or if I want to use my formula, my change in y or my change in x formula, because I don't like counting. The coordinates here are 0, 2, and the coordinates here are 3 and 9. And then again, notice that the x values here, or the x values in my given interval, I just found the corresponding y values on my graph, and then use my formula. So using the formula, y2 minus y1 would be 9 minus 2, x2 minus x1 would be 3 minus 0, and I get the same exact 7/3, just a matter of which way you would prefer to calculate it, okay? And again, a positive makes sense. That's definitely an increasing portion of the graph, okay? So there's the average rate of change using a graph. The next two examples, we're given a function instead, but we need the same information. Now, I could absolutely create a graph here if I want, but I have my interval, and oops, highlighter, my interval, that's my given set of x values. To find the y values here, to find the outputs here given my inputs, I can just use the equation. So I'm going to set this up in a little table. I'm going to make a table. I have my inputs, and I can find my outputs, which are called h of x in this case, by just plugging those inputs in. So it's saying start at an input of 3 and end at an input of 8. So if I actually input the 3, right, find h of 3, then I would have the square root of 3 plus 1. That's the square root of 4, which makes 2. So there's my first endpoint on the interval. And then if I input the 8, so find h of 8, I'd have the square root of 8 plus 1. That's the square root of 9, which makes 3. So that's the second endpoint on my interval. So I have one coordinate here at 3, 2, and I have one coordinate here at 8, 3. I can use those two coordinates now to find my slope. So my slope is going to be y2 minus y1, that's 3 minus 2, over x2 minus x1, that's 8 minus 3. So 3 minus 2 is 1, and 8 minus 3 is 5. That makes my average rate of change over that interval. It makes the slope of my secant line through the endpoints on that closed interval 1/5. Okay, and hopefully a positive slope makes sense here as well. If we can visualize what this graph looks like, our square root function that's just shifted to the right one, if we're looking over the interval from 3 to 8, that's somewhere over here, definitely going to have a positive or increasing slope. All right, again, one for you to try. If you're feeling confident, pause the video and give it a shot. If not, let's see, we're finding the average rate of change for a quadratic function over the interval from 0 to 5. So again, I'm going to make a little table out of this, just nice to organize in the table. This function is called g of x. They're giving me the inputs. They're saying start at an x of 5 and end at an x of, start at an x of 0, end at an x of 5. I'm going to find my corresponding outputs. So I'm going to plug the 0 in, g of 0. That's a negative 0 squared plus 1, which makes 1. And then I'm going to plug 5 in. So g of 5 would be a negative 5 squared plus 1. And be really careful on this. Remember when you're inputting numbers, you want to use parentheses. I'll see a lot of mistakes happen with this piece right here. We are squaring the 5, not the negative. and exponents have to happen before multiplication. So we're not squaring -5, we're squaring 5 and then multiplying by a negative. So that's going to be a -25, and then when we add 1, we get a -24. So my second output's going to be a -24. Now again, I have my 2 points. So here's the first endpoint on that interval, here's the second endpoint on that interval. And now I find the slope using those 2 points. So y2 minus y1 over x2 minus x1. That's going to make a -25 over +5. That makes my slope a -5. And I'm hoping that makes sense as well. Visualize what this graph looks like. That's a parabola. It's reflected over the x-axis and shifted up 1. So the graph looks something like this. Over the interval from 0 to 5, this graph is definitely increasing pretty quickly. So a -5 should be making sense. It's pretty reasonable, if you ask me. Of course, in my skewed math teacher opinion, right? Okay, so that's finding an average rate of change. And the reason we want to do this is, again, because this is going to help us tremendously when we go to calculus. So average rates of change, they relate directly to calculus, right to calculus, through something called the difference quotient. So average rate of change relating directly to calculus, which is the whole goal, get ourselves ready for calculus. There's something called the difference quotient. Now the difference quotient, and you can kind of see a preview in the box there below, it's really just different notation for slope. And let me show you with the same picture we looked at earlier. So we're still looking at a secant line, right, crossing through the curve here. We're still using the slope of that secant line to approximate the slope of the curve on some closed interval. But we're going to start by calling this point, we're going to say this point has an x value of x. And then the second point here, we're going to say that's just that x value you started with plus some distance. So it's like h units away from x, so we're going to call it x plus h. So we started at x, and then we just added h to get to some point further down the line, okay? So we're going to call that x and x plus h instead of a and b, which means our output here would be f of x, right? Plug the input in, and my output here, and let's just pretend that these are straight lines, okay? My output here would be f of x plus h. So if I wanted to find the slope using these 2 points, so technically the coordinates here would be x plus h, that's my input, comma, f of x plus h, that's my output, and my coordinates here would be x, that's my input, and f of x, that's my output. If I wanted to find the slope through these 2 generically written points, my slope would be y2 minus y1, so it would be f of x plus h minus f of x, and then we would divide by x2 minus x1, and that would be x plus h minus x. And you can see in the bottom of the fraction, we have a positive x and a negative x that are going to cancel, and so that means we end up with just an f of x plus h minus an f of x in the numerator, that didn't change, but in the denominator, just an h. And this is what we call the difference quotient, okay? So the difference quotient, again, it's just slope. It is the slope of a secant line to a function that passes through the endpoints where that secant line, or it passes through the, I lost my train of thought. Okay, if I find the slope of the secant line that passes through the endpoints on some closed interval, that slope is this difference quotient, okay? I don't know what I was trying to say. I said it like 4 times pretty well, and then, I don't know, it's a lot of language, but I think you understand. I'm hoping you understand what I'm saying, okay? So this is just different notation, but still slope of my secant line to approximate or average out the rate of change to my curve, okay? So we're going to practice trying to just calculate this difference quotient because I think I mentioned this in the previous topic, but when we find derivatives, remember this is one of the key concepts that we look at in calculus, the derivative ends up being the slope of a tangent line, and we can find like a generic derivative of any function, and it ends up being an equation but if we want to find the derivative of a function at a specific point, we have to input a specific x value into that function. So it's kind of a similar concept here. When we go to find slope, it can be like an equation for slope, and then at a specific point, we can input and find a specific slope. So I don't know if that's making sense. It will make a little more sense when you start talking about it in calculus, but we're going to practice. This is basically using function notation, finding this difference quotient. It's going to be like a generic or like a formula for slope instead of an actual numeric value for slope, okay? So let's try it. We're going to try to calculate this difference quotient, which again is just slope. It's just going to look a little strange for our function f of x being 4x squared. Okay, so there's three pieces. First, I have to find f of x plus h, and then I have to subtract f of x, and then I have to divide by h. Okay, so those three pieces, that's what we got to focus on. So first, if I wanted to find f of x plus h, okay, what does it mean? Well, if I said to find f of 4, I know what that means. It means take 4 and plug it in. Well, same concept, okay? If I want to find f of x plus h, which is what I have to do first here, that means take x plus h and plug it in. So the first part of this, again, finding f of x plus h, we can just call this m because that's what it is. It's going to equal, actually we don't have to call it anything, although we could call it m. F of x plus h is going to equal 4 times, in place of x, I'm plugging in x plus h, and that's going to be squared. So that's what f of x plus h looks like. It takes x plus h and plugs it into x, 4x, okay? Then the formula says subtract. So here, subtract. Then the formula says f of x. Well, I don't know. I already know what f of x is. It's 4x squared. So I want to subtract 4x squared, okay? And if there were multiple terms, like if there was a 4x squared minus 1, I would want to make sure to have 4x squared minus 1 in parentheses so that the subtraction applied to both of those terms. But it's not, so I can skip the parentheses on this one and just call it 4x squared. Okay, and then on the bottom of the fraction, that's the easy part, we're going to divide by h. So h. So there's the setup. That's honestly half the battle. Now we're just going to do some algebra to clean this up. And in fact, I'm going to move this up because I think I'm going to need more space. Okay, so in the next step, I have 4 times x plus h squared, means x plus h needs to be multiplied by x plus h, minus 4x squared, divided by h. So this is 4 times, when I multiply this out, I get an x squared, an xh, another xh, which means I'm going to have 2 of those. So 2 xh's, and then I get an h squared. And then I still have my minus 4x squared, again, divided by h. Now I can distribute the 4. So now I have a 4x squared and 8xh, a 4h squared, and then a minus 4x squared, still all divided by h. Now on the top of the fraction, I got some terms that are going to cancel. 4x squared and negative 4x squared, gone. So that just leaves me with these 3 terms, but notice all of them have an h, which means I can actually divide the h here and divide the h here, or reduce all 3 of the terms by h. So what I'm going to be left with is, if I reduce this term by h, or divide by h, I'm left with 8x, plus if I reduce this term by h or divide out the h, I have a 4 and an h left. And there it is. Okay, that is what we call the difference quotient for the function 4x squared. And then later, when you get to calculus, this difference quotient is something we use in conjunction with limits to find the slope of a tangent line at a specific point. Okay, this actually does represent the slope. It represents the slope of this parabola, this quadratic function, at any generic point, and if we plug in a specific x value, we can find the slope at that specific point. It's just really hard to explain. So I'm doing my best here, but if you can at least manipulate the algebra, you're going to be in good shape getting into calculus, okay? Let's look at one more example, and then we'll call it here. So f of x equals 1 over x. This is our reciprocal function, our parent rational function. So we're going to find the difference quotient by first finding f of x plus h. That means x plus h has to get plugged in there for x has to replace our input. So f of x plus h is going to be 1 over, instead of x plus h. And then I want to subtract f of x. Well, f of x, that's just our function. So I'm going to subtract 1 over x. And then that is going to be divided by h. And now we have a complex fraction. So half the battle is getting everything plugged in, which actually wasn't too terrible here. But now we got to clean up here. We got to use some algebra to simplify. So if I want to simplify this, there's a few approaches we can take, but we need to do the subtraction in there. We don't want multiple fractions to be in this fraction. So if we want to do the subtraction that's in the numerator, I need a common denominator. And remember, common denominator, where single terms are going to be considered separately from those binomials. In essence, I'm going to have to multiply this fraction by x over x. Remember, multiplying by 1 as to not change the value of the fraction. And I'm going to multiply this fraction by x plus h, so that now both of my denominators are the same. They both have a factor of x, and they both have a factor of x plus h. Oops, went too far. So what I'm looking at now is x. Well, we got a common denominator, right? So let me just, in the numerator of this complex fraction, I'm going to have an x plus h as my common denominator. And now, let me erase this. All right, so this common denominator, I just brought that down. And now in the numerators, I'm bringing down the x times 1, which is going to be x, and then a minus 1 that has to distribute to both of these. So it'll be, change colors, minus 1 times x and minus 1 times h, so a minus x and a minus h. And remember, this is all still over the h that's in the denominator of the complex fraction, okay? So I can obviously clean up the top some more, because x and negative x are going to cancel. And so if I have a negative h over x times x plus h, and it's being divided by h, which is technically h over 1. This looks so silly over here, lost all by itself. Then I have the quotient now of one fraction, or two fractions, one fraction divided by one fraction, so I can multiply by the reciprocal. So this is going to be equal to the negative h over x times x plus h is going to stay. So I keep that top fraction the way it is. I change the division in the middle to multiplication, and I'm going to flip that second fraction so it becomes 1 over h. And then my h's are going to reduce. And so I'm left with my final result. The negative is still in the numerator. The negative is still in the numerator times the 1. So it's going to be a negative 1. And then in my denominator, x and x plus h. And that is the difference quotient for our reciprocal function, our parent rational function. Okay, and then again, when you get to calculus, you're going to use this in conjunction with limits to find the slope of a tangent line generically, or the slope of a tangent line at a specific point. Okay, so hopefully, again, you can muddle through the algebra. That's really what we're trying to work with here in preparation for eventually going to calculus. But as always, if you need any extra help or you have any extra questions, please reach out. Until next time, take care.